Alright, C495. Now, assume that our electro system is completed. Quickly, you'll be interested in how much material you use it. So go to display and then we're gonna put out all the material takedown. So show table. Let me just see. So miscellaneous data material list. Let's see, material list by object and type. All right, so let's turn on. I'm gonna choose by object. So here, the first table, you see the column kips, beam kips, and we have some, concrete beam as well, right? Bracing, which is steel. You see that by the material. So you can just sum them up. So Control C. I'm gonna open the Excel spreadsheet and see. If you copy it, you can, let's see, is there something we can throw data? We can throw it out like this, right? Or better, is there a better way? So I think it's what we can see, we can sum them up, this steel material all together, right? This model, you can sum them up, so it's a total kips, right? So the column brace beam, still we use this, divide by 2 makes tons, so 30,000 tons of steel, right? And then also the concrete, so this is a concrete beam, concrete wall, I think our composite. So probably I'm gonna first of all sum them up to our beam, right? This is kips, remember that. And then wall, sum them up. And this is the floor, so kips. What is this guy? I do have some thought of also the concrete slab inside the core wall. That's why I have this number. So this is all the kips, right? For the wall, slab, and beams. Let me see this. What is this floor? Let me double check. So I'll just take a look at what. Okay, seems like this is the slab. And metal deck. And do I have a double elements? Section property. Oh, this one might be. Accidentally I include this. Okay. So this model, I'm gonna just fix it. So I'm gonna go back. I think basically this supposed to be opening element. So I'm gonna choose change to all floor. I'm gonna click, 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 click. Basically, I'm gonna show this. This element, right? Supposed to be opening, not floor. So I'm gonna assign the shell to opening, right? Opening. It's not supposed to be slab. So I'm gonna just take a look at it. Yeah, see. So we have only some also slab and opening. So I'm gonna rerun it. I'm gonna get the new material properties. So this number, obviously, this is not really a one. Doesn't exist because this is all opening. So you can just sum them up, all the weight of the concrete. Because the concrete weight is 150 pound per cubic feet. So if you sum them up, or maybe wall weight, total weight of the concrete divided by this is going to be a cubic feet, right? Right, this is, no, actually this should be multiply by 1000 because it's cube, right? So make this a pound divided by 150. So this is a cubic feet. I think our concrete wall material, this is a cubic feet. I think so we can usually convert it to the cubic yard, divide by 27 or something. Same thing that the beams, we can sum them all the concrete weight, right, for the wall and slab, and we can sum them up and divide by 150, and we can get the total volume of the concrete for wall and beam. We can do that for floor because this is weight, right? This is lightweight concrete, so you need to divide by 115, right? So basically, you're getting this, but you're gonna multiply 1000, multiply by 1000, divide by 115 because it's lightweight concrete. So this is cubic feet again. So this is slab total concrete volume. This is just only wall. This is still tonnage. So basically concrete wall and beams, you can sum them up and divide by 150 because they're normal weight concrete. Floor slab, we assume they're lightweight concrete, so you need to use total weight divided by 115 so that you can calculate this. So something that material takeoff, you can use it. So going here, since everything's run, maybe I'm gonna just pull it out again. Show table, material list. I'm getting this table and maybe paste right there. So we have only material. What is the easy way to store it? Data. Okay, somehow still. Okay, so this is something summations, and the wall and beam, you could sum them up all, right? So you could just calculate total weight of the wall and beam, divide by density, concrete weight, and get the volume. All right. Okay, since we just talked about the material takeoff. Now, what we're gonna do, since this model is ready, we're gonna transfer all the data, column and wall reactions from this model in order to create the foundation model, right? So we're gonna export. So story as a safe version 12. So we're gonna export all the reaction at the base, which means our support. So we are gonna export all the flow loads and load from above. So this is something that all the column reactions should be transferred through this. So which load cases? Maybe we're gonna this is auto sequence loading is representing that and STL. So I'm gonna export live load. We don't need a construction dead load. This is only just composite beam. So I export dead load and STL is part of auto sequence load and live load and the wind load and live the wind load X and Y. So I'm gonna export all the data, right? So that is export to the safe.f2k file. So I just export. So now second is I'm gonna open the safe. This is a foundation and slab design software, same CSI product. So I'm gonna click the file and new. Wait a minute, do I have to hold up? Do I have to open it or just I'm gonna just start from blank. Go to import and save f2k file. Basically, it reopen it. Where it is? Oh, the folder I forgot. Where did I have it? Okay, so let me go export. Story 2, base, second. Okay, here it is. Here is a link. I saved that. So go to save, Ctrl V. Okay, here is my file, f2k file. So I'm gonna open the data file for save, which you're gonna see only just start and all the reactions. So let's see. When you open, import all the data, you only see minimum informations, but we're gonna take a look at what kind of information we're getting. So show the load, the joint. Instead of that load, I think I'm gonna click the auto sequence load. So you see that, oh, let me see. The load from above, yeah, you see that vertical loading, right? 2,367 kips. So all the load is transfer, so you should be able to have all the reactions like this. So this is all the data transfer, all the reactions from all the column and the wall. So this is the column reactions. You maybe double check the unit as well, but I think I'm gonna leave it. So now what I'm gonna do is I'm gonna draw the mat foundation first. Yeah, we maybe have to define the material as well. Let's see, default is 4,000. If you wanna do exercise, why don't you do that? Create another one, right? But here you have to do square root time, square root 5 divided by 4. So you can create a new material. So I create the 5,000 as well. So also I'm gonna create the slab. This time is mat, right? Defaults. I'm gonna change default to mat type. Maybe we're gonna assume that this is maybe 8 foot thick mat, 96 inches. So let's say 96 mat. I'm gonna use a 5,000. Right? This is just an initial the kind of trial. So I'm gonna using this draw the 2-point method. I'm gonna click 1 point. Oh, wait a minute. 1 point and drag and drop. So I draw the mat foundation. Oh, actually I didn't choose. Oh yeah, this is only default section property. So I draw this. So I draw the geometry, right? If you want to see extrusion, see the extrusion. See the thickness, right? Thickness. You want to just extrusion for the wall element. Yeah, there is a wall element. Typically, this is a two-dimensional software, so you're not going to see more all the column geometry profile, but I think that is not. So you can just generally see the geometry, right? So I think, but one thing that because we explore and the column reaction should be on this, because somehow basically we cannot put the column at the edge of the mat. Obviously, our mat should be bigger, right? So, wait a minute, I'm gonna turn back. Turn off that. Turn off the extrusion. So what I need to do is typically this mat has to be expand. So I'm gonna go edit. Let's say expand the shell elements. Maybe I can expand about 60 inches. So I expand this, right? So when you see this, turn on the load, column load. Column load is located at in the middle of the mat foundation, right? So now Next one is kind of boundary conditions. Initially, maybe we need some geotech information from here. If you are interested here or pretending as a geotech engineer, you should be somehow grab a reference book and find out what is the soil spring constant for this mat. Things in the beginning, first, I'm gonna just assign the default spring constants, like to go to sign and shell. And there is, where is that? Okay, area spring, right? So this is area spring. We have a one default soil one properties. This is some minimum spring constant. So we'll just try. Let's see how it works. So I'm gonna apply the soil constant, spring constant. Wait a minute. Yeah, soil so spring constant, which is boundary condition. This case is we treat this mat as most likely our matrix. This have a lot of continuous spring, vertical spring to support this mat foundation, right? So this number, soil spring constant, we need to really get the information from geotech engineer based upon all soil data and their boring and analysis. But we're gonna just use default and we'll revisit it. But I'm gonna run this model. Let's see. I'm gonna save it and run the model and see whether this model can run and show us in general overview of behavior of mat. All right, the first run is show the deflections, right? So, yeah, deflection. The first thing I'm interested is I want to see the soil bearing the stress, something like a spread frame. So let me see. So stress is it the display soil pressure, right? Due to the maybe dead load. Maybe let's choose our total dead load, right? Dead load plus proposed dead load. So see, I just look at it. Maybe we need to change the unit because this is pound. I'm gonna change pip and fit, right? So I'm just look through it. Okay, at the bottom, we are experiencing total 10 KSF, kip per square foot. But as move, and then it goes down to 5.1, right? Maybe 3 at the corner. Because we have a heavy weight of the kind of concrete wall, which coming down and also concentrically loaded, so that all the soil bearing will be migrate or disperse and reduce to the from center to the edge. So this is soil bearing stress, which I think if you remember that you have a spread footing, I think so we assume that all the footing is work like a rigid body, so that we assume that using uniform load distribution based upon your column load. But since we are dealing with a huge mat, we need to use a continuous kind of spring. When you go to sleep, first in the morning you feel something your back or some place is kind of pain. That means your mattress somehow deflect, right? Non-uniformly. So your body probably experience some strain and stress. That's why you may have some pains. Which I think that's why soil and mat has working and perform something similar way. So if soil is soft, I think obviously if soft work like a soft mattress, you maybe experience more back pain. But this is soil is firm, and your deflection is a little more kind of relatively uniform, rather than just dishing effect like the deflection at the middle highest point at the middle and a lower point at the end. So it's actually representing that this plate's gonna bend more if you have a small soft soil spring constant underneath. All right, so I think this is the second step. I want you to build this math foundation. We'll just follow this video, and then why don't you create the safe model. After that, what we're gonna do, we're gonna check the old soil bearing pressure. We're gonna set up some design strip, and design also we're gonna set up some load combination so that we can design the mat and the reinforcement in both direction, X and Y direction. All right. So I'm gonna just stop this video and upload it, and I'm gonna continue maybe with a little more detail for math foundation, the next video.